So this was what I was saying before, or what I was going to say before. This is the first time I've put together a lecture about what would be helpful for the virtual memory lab. And so I'm not sure how helpful it will actually be yet. So two things. One is when you're finished with the virtual memory lab, I would love some feedback if there were things that you would specifically suggest is added to this discussion that is not presently in it. And secondly, if you have questions or there's anything that's not explained to your satisfaction in the lecture, then please let me know, because I'd be happy to improve that as well. This lecture did not get as much time as I had hoped to devote to it, because my mom had computer issues. And, well, when mom has computer issues, you take care of your mom. So I made sure to do that. Let's see, what else did I want to say? I think that's about it for now. We'll go ahead and just dive into this. This is the Pintos Virtual Memory assignment. It's one of the two hardest ones, but honestly, when you look at it, you realize functionally this isn't. I would say it feels to me like it's about as hard as the threading lab. So I don't know that it's actually that miserably complicated. And so I think probably a lot of the difficulty stems from not designing before you implement, not taking the time to carefully design before implementing, and also trying to do too much and then not testing properly along the way. And you'll notice that that is a theme in the discussion. What I will also tell you is that this is not, I'm not fully sketching out a design. Part of this assignment, is, as you'll see in the write-up, is you have a lot of flexibility to decide how you want to do things. And I'm not going to violate that by telling you exactly how to do certain things. I'm going to give you certain big hints based on the solutions that exist for Pintos and various other details. But honestly, the way that I view this lecture is it's kind of an aggregate or a synthesis of the material in the assignment write-up and in the code base itself. So I'm hopeful that this will help you a lot. Pintos does have virtual memory because remember, programs can only contain virtual addresses. So the kernel has to have some kind of virtual to physical address space mapping. So really what we're talking about is implementing disk-backed virtual memory so that we can page things in and out of page frames. So we have address space isolation that already exists in process.c and a few other things. And user program loading is also described in there. So there are certain things that you have to build on, which is really nice. You have a swap partition, which you probably haven't used until now, but that's going to be one of the early things you have to do in Project 5 is initialize a swap partition. And then that's the location that you can save virtual pages to and then load them back. There's also a bitmap implementation, which is useful for both the file system and swap storage. So you'll probably encounter the bitmap partition, the bitmap implementation again on Project 6. Okay. Also, one of the great simplifications, and this is a big hint that I hope will be very helpful, is that you don't have to do anything crazy with synchronization. I mean, some might argue that anything involving synchronization is crazy, but at least you don't have to create new primitives and you don't have to do crazy things like priority donation or anything like that. You can rely on the standard Pintos primitives for implementing that part of the assignment. Okay, Project 4 tests. This is why I keep saying Project 4 needs to work really well. The system call stuff should continue to work. It'll continue to run those tests in both Projects 5 and 6. And so that's one of the things that you'll notice. That's why I tried to encourage you to get that working as well as possible. Like I said also, one of the early things that you'll notice in the assignment write-up is try to get any missing Project 4 tests passing. They're weighted less, but they will still deduct from your grade if they're not passing at the end of Project 5. So, whatever. It's not the end of the world. Multi-oom is the one that everybody hates because it's just... and somebody actually asked a question on Piazza about how you debug multi-oom, and that's a really difficult one to debug because we have very little debug information collected by that kernel allocator. And that is another one of those examples of where having an OS with built-in debugging facilities is really nice. And Pintos has none of those things, and so that makes it quite difficult. Most of the people coming through this class at Debug Multi-UM basically just stare at where they allocate things and where they free things and try to figure out what kinds of objects or what sizes of objects they may be leaking. So, and of course, yes, sir?
What sort of built-in, what do you mean when you say built-in debugging?
Built-in debugging tools, like if you're the kernel, then you should be able to record or monitor some information about who's doing allocations within the kernel. So for example, if you have a debug mode that you can switch your kernel allocator into where it says, remember every place that things are allocated, types of objects. This is one place where I prefer zone allocators because if you're able to keep track of the kinds of objects that are being allocated, and then you can figure out what is not being allocated. Then you can look at the places that they're allocated, make sure that the places where they should be deallocated is being called at the appropriate time, and so forth. So typically what it would be is some kind of kernel internal tracing facilities that you could turn on and off for debugging. A lot of times people don't spend time creating those kinds of facilities, and then they end up taking more time on their debugging than they would have taken to write the facilities in the first place. That seems more and more to be what people are finding in these complicated systems. A simple version that you see in CS124 is students who don't take the time to learn how to run the debugger, and then they start working on the kernel, and they find that they spend more time debugging than they would have learning the debugger and finding their problems more quickly. So, anyway, yeah. Hopefully that answers the question there. There's other really neat things that people are doing as well. Greenplum, I always get these people mixed up. Greenplum did the database. Green Hills does compilers, and they also have a formally verified operating system. They did the pizza for the threading lab, and it would be cool to get them out again for maybe the virtual memory lab. We'll have to see, but they have taken various strategies to try to create a rock solid, reliable kernel as well. So that's pretty cool. Okay, there's various things you can do. Anyway, Project 5, there are new tests because you'll have mmap, mummap, and a few other details as well. Tests that actually grow the stack, user space stack, and so forth. Okay, so here's what you have to do. Demand paging for loading program binaries. And what I say here as far as demand paging, this is pure demand paging. So that's actually one of the early things that's like the second step of the implementation, that basically you don't have any part of the binaries mapped initially, and only binaries are loaded into memory as page faults occur. So that's part of the implementation, demand paging for stack pages, but they suggest that you may want to allocate the first stack page for the process right at the beginning, because it will always fault. So why not do that? And, I don't know why you wouldn't then also just load the first page of the program binary, but that's what the assignment says to do. Memory map files. Interesting. This is a simplified version of mmap. This is not the full gory Unixy version. Notice I say here that memory map regions in the process cannot overlap, so you're supposed to give an error if you have two overlapping address ranges for mmap calls. Also, well, there's a third simplification here, which I'll mention second actually, which is that you don't have to worry about protections, memory protections. So every time you memory map a file, it's always read-write. That makes it easier. Finally, if two processes map the same file into memory, you do not need to worry about consistency. Again, Unix processes allow you to memory map the same file into two different processes, and it has to keep those two views of the file in sync. So one process writes to that memory region, and then we context switch to another process. It should have seen those writes even if they haven't hit disk yet. So you don't have to do that. So this automatically makes things simpler for you. Okay? You may or may not believe that, but I am telling you all these things because I think your implementation should leverage as much as possible to simplify things. Okay, so that's really nice. Yes, sir?
There should be an error if you memory map a file and it hits anything that was already like legit memory pages. That should throw an error, right?
I believe so, yeah. My guess is that the way, and again, it's unfortunate because sometimes you only know for sure by whether tests fail. But yeah, if any memory mapping request overlaps any other memory region that's valid for the process's address space, then it should generate an error. There's other errors as well that you'll see in the specifications, like if starting addresses aren't page aligned, and I don't remember if it says anything about the region size being page aligned, but you should look at those kinds of constraints. Because again, the great thing about Pintos is if there's a spec in the assignment description, there's probably one or more tests that exercise this. So you'll see a failure, and then you can just go read the test and fix it. Yeah. Okay, does that answer your question? Okay, good. Let's see. Simplifications again. No shared libraries. Phew, everything's statically linked. That'll make things really nice for you. You don't have to think about this stuff. Also, no dynamically resizable data segments. Now that's so with the caveat that the stack is technically a dynamically resizable data segment, but that's really the only thing that can be resized in these processes. A lot of times people ask the question, what do I have to do for malloc? No user space malloc. Okay, you don't really have to think about that. Basically, the way that the tests work is if they want a lot of space, they put it in BSS. Okay, and then it's statically sized, and you take care of it at load time. So that's really nice. That'll simplify life a lot. Concurrency. So there's really only one concurrency requirement. And you can comb, again, this is what people do every year, and so this is why I want to try to aggregate this all into one place. If a page fault requires I/O to complete, then it shouldn't block anything that doesn't require I/O to complete. That's the one big requirement for concurrency. And you should not try to do anything more sophisticated than this unless you really love solving complicated problems or hate sleep. It's like if one of those two things is your problem, then you can go ahead and try to be better than this. Okay, but the reality is, there's actually two realities here. It's not hard to satisfy this requirement. You basically need to make sure that you don't have any large, long-running operations that you're performing that may acquire a lock and then do some I/O. Okay, so that's kind of basically the only thing. If you do need to hold a lock, which you probably will when you're performing I/O, then make sure it's a lock over something small. So you want to make sure you achieve fine granularity when you're doing I/O operations. Don't have a coarse grain lock when you do that I/O. Okay? So that's kind of the big deal here. The other thing that I'll mention, and this will become even more important for next project, is that disk IOs are already serialized. You can't have overlapping disk IO in Pintos because it doesn't have DMA transfers. It doesn't know how to do that. When you want to do a disk IO, it sends bytes to the controller, and then it basically puts the requesting kernel thread to sleep until the controller fires an interrupt, and then it wakes up the kernel thread. So this is nice because it means that other kernel threads can run while a kernel thread is blocked on I/O, but it also means that disk interactions never overlap. And so A, that it really simplifies your life, and B, doesn't allow the OS to do anything efficient for I/O. A lot of times, and I should actually give a lecture about this. I don't know if I'll have time to prepare it, but a lot of times operating systems try to schedule disk reads and writes so that you get these nice linear sweeps of the disk platter with the disk head, and they're called elevator algorithms. Not so important with solid-state drives, but if you have a spinning magnetic disk, that's actually really important for performance. Pintos can't or doesn't or won't do any of those things. Okay, extra credit. There is an extra credit option, but it's weird. It's not. It's do shared memory, but it's not the kind of shared memory you might think of. So, extra credit is read-only sections of program binaries are shared across processes. Okay? That's really all it is, which means you don't have any read-write shared memory. You only have read-only shared memory. And, yeah, I mean, and it's funny because this actually complicates things enough. Because if you think about it, when a process terminates or when a page is evicted, well, now you have to think about the potential that other processes may be using that page frame in their page tables. And so you have to think about all the implications of doing this. So this is complicated enough. But you'll notice even read-only sections, like you can't do the read-write sections. You can't share those. I mean, that should be really obvious because if you share the read-write sections, then one process will see another process's changes to state. You know, like .data. You know, I have my global variable that's initialized in there and it's read-write, and one process writes to it, another one can see it. So that's obviously not going to work. So this is the only thing that you can really get extra credit for. I think it's like 4 points, if I remember correctly, the scoring. I'd have to check, but if you really want clarification, ask me and I'll look it up for you. But I wouldn't spend a ton of time on this unless, again, you just really are raring to explore virtual memory more. Okay, so any questions on the requirements? So that's basically what you have to implement. I wanted to give you some overview of this stuff. We've already talked about some of this, but some of it is Pintos specific. We have frames or physical pages, which are basically what store virtual pages for a process. Okay. So they all have a specific page size and an alignment. And pages, which are contiguous regions of virtual memory. This is actually straight out of the assignment, so I'm just going to introduce you to their definitions so that you're clear on all that. And since we're on 32-bit, we have a two-level page directory structure. And so in the thread type, you'll see a field in there that's actually used for the page directory for that kernel thread. So when we go into user space, when we transfer into the user process, that's the page table that's switched to start doing address translation. Now, what's important about this? Well, we have two levels. So we have a page directory and then entries in the page directory. There are, I can't remember, how many are there? Each entry is what, 4 bytes, and it's 4. So we have 1,024 entries hanging off of the page directory, and then each one of those can be a page table with with 1,024 entries in it. Okay, so it's a two-level tree, pretty straightforward. We have swap slots as well, which again these are on the swap device. More simplifications are you don't have to worry about bad sector identification or addressing. So that's where a bitmap will be really easy. Is this swap slot used? Is it not used? And so you'll just have a bitmap you can use to find an available slot. You don't have to worry about detecting if it's got errors or anything like that. You can just assume everything works properly. So we're trying to simplify things as much as possible for you all so that it will be doable in 2 weeks by 2 to 3 people. Okay, this is x86, IA32 address space for Linux processes. Pintos, remember, does use this. We've already talked about this because you would have had to know this for the system call lab. But there are some notable simplifications here. First of all, we do have the same boundary between user space and kernel space that's in Linux processes on IA32. It's defined as FizzBase, and you'll notice this over and over again in the write-up that it says use FizzBase, don't hard-code that constant, because they want to be able to change FizzBase and have it still work. Now they don't, so don't worry about it, but they say you should support it if they change it to whatever. It's like, okay, yeah, that's nice. Just use FizzBase. It's like good programming practice anyway. There is a lot of stuff in vAdder. You should really review vAdder because that's going to become pretty important to you this project. Okay? But that's also where FizzBase is defined if you want to see that stuff. Okay, this is what I mentioned before. We don't have any shared libraries. Okay? And we don't have any user space malloc support. So basically, we have only the parts that I have described here that's below FizzBase. User stack and the program binary. Okay? And everything else is basically nice blue ocean that you don't have to think about or worry about. I guess except for mmap calls. Now, Pintos has a limit on how many frames it will use. It has a couple of simplifications as far as frames are concerned. It always uses up to a maximum of 64 megs of physical memory. Now, the emulators allow you to say how much physical memory to run with. So, I vaguely recall, I couldn't go back and check. I didn't take the time to do so. But I believe that some of the tests are run with only 2 megabytes of physical memory. So you can figure out how many frames that would be. But it's always capped at 64 megs. So you can do the math to figure out how many frames maximum could be initialized in the system. Now, why am I telling you this? Well, mainly because whatever design you come up with should work for at most that many frames. And sometimes that helps in your design to say, okay, this data structure makes sense, is not going to be obscenely large or something like that. The number of frames actually available in the system is in this variable init RAM pages. That's actually initialized in the startup code that runs immediately after the bootloader. So this is some of the very first code that runs to figure out physical memory size. This is still in, it's actually still in 16-bit real mode, and it calls a BIOS operation to figure out what that size is, and then puts it in init RAM pages. Okay, there were a few other things that I wanted to say. Pintos keeps all frames mapped into kernel space. Okay? I couldn't figure out a good picture to draw for this, but you can imagine that you have these physical frames, and they're all physically contiguous. So they start at address 0, physical address 0, and they go up to how much memory, physical memory, is available on the system. All of those frames are mapped into kernel space starting at physbase. That's why it's called physbase. Okay? So starts at physbase and then goes up. You have a virtual frame mapped into the kernel for each, or I'm sorry, a virtual page mapped into the kernel for each one of those frames. And that never changes. Okay? So those frames are always available in the kernel, and you can reference them by virtual address, physbase plus the physical address. Now this is where the functions of vadder will become useful, because you'll have things like p to v and v to p, and what that does basically is adds or subtracts physbase onto those addresses to go from virtual address to physical address or physical address to virtual address. Because you do not store virtual addresses in page table entries. You store physical addresses in the page table entries. But the nice thing is inside your page fault handler, when you're loading data into a frame, well, you can use the kernel virtual address to load the data into the frame. No problemo. Okay? So that's how this stuff is going to be important. When you're loading data into a frame, well, it's already in the kernel address space, so you can easily load it. Okay? The other thing that so real operating systems totally don't do this. That's just probably should be obvious. But if you have a situation where 1/4 of the virtual address space is handed to the kernel, then it would stand to reason that not all the frames will actually fit if you try to do this in real life. And so real kernels have to do a lot of juggling and careful management of physical page frames, even though they're not necessarily always mapped into the kernel's address space. So this is a simplification. The other thing to mention is that init RAM pages, you guys probably saw there's a kernel pool and a user pool, and there's like PAL user and PAL, I can't remember the other one, when you're allocating page frames. And that pool is divided in 2. So half of them are for user pages, half of them are for kernel pages. Again, real kernels don't use nearly that many pages. They're going to devote the vast majority of their pages to, or their frames to user space applications. So that was another thing to mention. Okay, so yeah, you can manipulate the contents of any frame in the kernel. Do I say anything else here? Yeah, and you can move back and forth between virtual addresses, kernel virtual addresses in particular, and physical addresses, because page directories and page tables need to have physical addresses. Okay. Any questions about any of this? So this is going to be important for how things work. So like I was saying, processes have their own page directories. This is an interesting detail and sometimes confusing to students. So while it probably won't be immediately relevant to any of your implementation, I still wanted to cover it so that you understand conceptually how everything hangs together. There's a new page directory created for each process, as one would expect. We initialize that. That's in pagedir.c. There's a special function that goes ahead and does that. What it does is it makes a duplicate of an initial page directory that's set up at startup time. Okay? So there's various things that initialize. You guys, again, probably saw some of this when it came to argument processing and so forth. But you have threads init.c, and it has a function called paging init. And it initializes this data structure called init pagedir. And you'll notice that it sets up a page directory and does all the kernel address mapping. So the first 64 megabytes of address space, or up to that, is mapped into the kernel, starting at fizzbase up. Okay? And so we have various page tables hanging off of that. Now you'll notice that this is only kernel page mappings at this point. We don't have any user process pages yet. Okay? So the kernel is running merrily along. It's using init pagedir. When you actually start creating processes, then what happens is the page directory is copied, but that's the only thing that's copied. And so what you actually end up with is the process's page directory is referencing the page table nodes that the kernel has. Okay? So they're actually, you think of them as two separate trees, but in fact, they're two separate tree roots that are sharing a big subtree that corresponds to the kernel address space mapping. Okay? And so then what happens is when the process is running, you can see other page tables will be added as the user process address space is fleshed out, to load the program and so forth. So those are visible off of the process's page directory or the kernel thread's page directory, but they're not visible off of init pagedir. So that's the interesting thing. It's really clever, actually, how this is done. But this is kind of what you end up with. Various processes, all sharing the kernel address mapping, but having their own user space address mappings. So while you would normally think of these as separate trees, in fact, they actually share a big subtree that's for the kernel. Okay, so like I say, all processes share the same page table for the kernel space memory mappings. This is nice because it doesn't matter what process I'm in. If I need to allocate more kernel pages for whatever reason, I'm doing kernel allocations, or I'm updating kernel data structures like your frame table or so forth, well, that'll all happen in the kernel page memory mappings, and all the processes will see that because they all share the same part of that page directory structure. Okay? But, of course, if one process adds another user page, let's say the stack grows, and so we have to add another page. I should be more specific. You're adding a virtual page backed by a frame into that process's address space. Well, that affects the process local page table structure in the page directory. It doesn't affect something that everybody sees. Okay, does everybody understand this? So this is one of those things, if you're ever staring at this at 4 in the morning, wondering why some bug is occurring, and suddenly realize that, wait a minute, I'm making a change in the kernel and I don't know how everybody sees it, this is how. Okay? I'm pretty sure that every OS has to solve the problem in the same way or in a similar way. Otherwise, managing the kernel information becomes really difficult. Okay, implementing virtual memory. I feel like this is actually a really straightforward lab, and the reason I do is because if you sit down and ask the question, what happens when a page fault occurs, and you trace through all the details of that answer and develop it into a full picture, most of the things you have to implement fall out of it really easily. Okay, and probably Michael and Bobby are perfect people to ask this about, because I think they took like 6 hours on the virtual memory lab and had a perfect implementation afterwards. So I imagine that this is why they were able to do that. They just sat down and designed it carefully and considered all the aspects of it and then just implemented it carefully as well. So what does the page fault handler need to do? First question. Faulting address, is it even valid? I need to be able to figure out the answer to that. Okay? If it is valid, then what data actually lives at that address? Because that informs what I need to then load into memory. Okay? So that's the first question, is the faulting address valid? Second one, I need to find a page frame for holding the page that will live at the faulting address. Okay? So that may mean I need to evict another process's page. Okay? Third one, load the data that needs to go into that frame from wherever it should come from. Okay? And then the fourth step, install the frame at the virtual address corresponding to the faulting address. Now remember, what frame or what virtual address will I load this at? Well, I'll take the faulting address and round it to the round it down to the closest page. That obviously should be the page that it should be for. Okay? So this is basically it. This is your page fault implementation. But if you look at this, there's a lot of little nuances to each one of these steps to think about in your design. And again, I'm not going to spell all of them out, but I'm going to actually show you what I think are the most important parts to consider so that you can then sit down and design software that implements these things correctly. Okay? So, one interesting little detail is that you'll notice page fault handler will probably block an I/O. If I evict somebody else's page, then that's going to probably incur I/O. If I am loading a page from disk, then that will incur I/O. So here's the weird thing. This is inside of an interrupt. If I'm doing I/O, then I'm going to be blocking. Am I allowed to do that? Is that okay? Well, the interesting thing here to consider is who caused the page fault. It was not hardware, it was a user process. And so that's an important detail because this is actually occurring in process context, not interrupt context. The way I like to think of it is this is just another way of a user application to get into the kernel. It's just that it doesn't know. But the kernel's carrying out something on behalf of the process. So it's okay for the process to be blocked. Okay? So it's okay for this operation to take a long time. It's okay for it to block on a lock. It's okay for it to block an I/O. This is all perfectly fine. Okay? So I did want to mention that because it seems a little weird at first when you have an interrupt handler doing a blocking operation. But this is fine. This is normal because you're actually operating in process context at this point. Interrupt handlers shouldn't fault, I think is a good assertion, probably, for most OSs. I should say, yeah, hardware interrupt handlers should not fault. Okay, so yeah, while the fault's being resolved, other processes can run. So question, is the faulting address valid? And so this is one of the things we already talked about in the discussion of virtual memory leading up to this project, but there just is not sufficient information in the page table structure used by the MMU for implementing the abstraction that we want. And this is what most OSs run into. The hardware MMU's page directory structure is not sufficient for implementing the entire abstraction. And that's kind of a nice thing. The MMU does what it needs, and then if an OS wants more sophisticated stuff, it can add that on top. Okay? So what this means is that almost always you have to have supplemental information describing at a higher level the virtual address ranges. So we have a supplemental page table. This definitely puts the mental in supplemental. So yeah, and basically you need to think about what is the abstraction that the OS wants to provide, because that again informs what goes into the supplemental page table. Okay. Also, typically the supplemental page table describes the entire address space of the process, not just what's currently in memory. Okay? And part of the reason why is because when we page things out from a process, a lot of times another process is the one doing the paging out. Okay? And so the less data structures we have to hit, the fewer things we have to do to page things out, the simpler the system is. And so by having the entire virtual address space described completely, and just having that always be the picture, then and not modifying that based on page ins and page outs. It just keeps the design a little bit simpler. So supplemental page table will be initialized at process startup based on the binary, and then it will also be modified by mmap and munmap calls. And also, if you will, a third reason why it would change would be for stack growth. But beyond that, that is what causes the supplemental page table to change. Okay. And so here's the goal. It should be fast to determine whether a virtual address is valid, and if so, what should reside there. I'll give you a giant hint, which is not that giant because it comes straight out of the assignment. The assignment basically tells you about two data structures. It's like, hey, Pintos has these two things as a bitmap. Bitmaps are really cool, hint, hint. And then it also says hash tables are really cool, hint, hint. Okay? Should really think about hash tables for this. I'm not going to, now I think that one of the questions in the design doc is why are you using whatever data structure you're using? Okay? So you should think about why is a hash table better than like a linear array or a linked list? Okay? Should be an easy question to answer, but you really should include an answer to that kind of a question in your design doc. Because, yes, linear arrays can be fast to index into. How big will it need to be to completely describe an address space? How fast or how slow is it to look things up? So you have to think about those things. Okay, any questions on this part? All right. Again, developing this picture of what happens during a page fault will answer so many questions for you. Where does page data initially come from? It's the first thing you have to figure out. Okay? I run programs, and so clearly the program needs to describe what the program text is, initialize data, initialize read-only data, how big should BSS be, and so forth. Okay, so we have these sections of the ELF binary. Now, we never really talk about ELF, which is weird because, you know, in CS24 and 124, it's really important. So I want to find out if anybody has any questions about any of these. But basically, in the ELF format, it says here's a starting address, and here's the size, and here's the file offset to load this data from. Those are the three things. You'll see this in process.c. Starting address, amount of bytes, and here's where to start loading it into the address space. Okay, so that's one place where we need to load data. Important thing, when we evict these things, then we cannot save them back to the binary. That really only matters for .data, because .data is the only one that's read-write. .text and .ro data are both read-only, so we could evict them and just throw them away. We don't need to worry about saving changes. So again, you should be thinking about all of this stuff. This informs what should be stored in your supplemental page table. Then you have the anonymous file, which is our nickname, Unix's nickname for zero initialized memory. So stack pages, for example, and BSS. Okay. BSS stands for block segment start, I think, if I remember correctly, which is an anachronistic name. I can't remember offhand the history of that name. But again, it's described in the ELF file. It says, here's where it starts, here's its size, but then it doesn't say anything about what file offset. And that's on purpose. That's so that BSS will just be initialized to all zeros. Okay. And then you have memory map files. Okay. So they're loaded on request of user applications. And in Pintos, we always must save changes back to the original file. Okay. So you can imagine in your supplemental page table, you'll have little descriptions saying this address range corresponds to a file with an offset and a size. Or it'll say no file and obviously no offset and size. Okay. And you may also say this is read-only. You may say this is globally visible, or you may say this is private, meaning that changes should not be written back to the file. So we have stuff mapped from files that should go back to the file, stuff that is mapped from a file that should not go back to the file. Okay? So you'll need to capture all these details in your supplemental page table. Now that's the initial fault. What happens next? So let's say we've loaded it once, so now it's in physical memory, and now we have to evict it, and then suddenly things are going to change slightly. So you have sort of this dual mode that these pages need to work within. Okay? Binary program data. Where's the program data or page data evicted to? Well, remember, .text is read-only. We could just throw away the page and reload it from the binary. That would be fine. Same thing with .ro data. .data, we can't save back to the binary because then everybody sees the changes. So we got to save that to swap. Okay? So again, you can go through this process of considering each of these circumstances you have to handle and think about how they're supposed to work. Anonymous files, zero initialized memory. So stack pages and BSS. Well, they don't have a file store backing them. That one's obvious. They always go to swap. Okay. Memory map files. Well, these ones are kind of nice because in Pintos, you have a simplified abstraction you have to implement. On Eviction, you can save them back into the backing store. That's great. Please do. That'll probably simplify your life a lot. Okay. So, and obviously, if you save a page to swap, you have to remember what slot it's in. So again, that's a hint about what needs to go in the supplemental page table. Okay, so hopefully this helps you see what kind of information should be stored in your supplemental data, and hopefully this will also indicate to you why this has to live outside of the MMU's page table. Now, one of the things that the assignment write-up mentions is advanced students can modify the page table entries, the MMU page table entries. I would say don't bother. Why? I'm not going to consider you to be not an advanced student if you don't do that. You're taking CS 124, you're an advanced student. So, but the idea there is like what most modern operating systems do, which is when you have the page table entry and it's not being used by the MMU, use those bits for something else. Who cares? You can just go look up in your supplemental page table what it should correspond to, and then do the right thing based on that. Okay, so that's what most students seem to do. I don't know that I've ever seen a student use the MMU's page table to store information. Why would you? Any questions? All right, so that's this part. Let's see, I want to make sure we get through everything. I'm a little bit concerned about time. So anyway, this all is part of what needs to go in here. Got to remember page eviction as well. That's another part of this picture. But we're talking about paging in initially, but when we evict, again, the kernel is doing this on behalf of a process, and so we need to have enough information to figure out where to evict it to quickly and easily as well. Okay, allocation. We have to be able to find a frame to hold a page being loaded, which basically means the OS has to know what frames are available, who's using frames. And it turns out that there may be a little bit more information you'd like to record about frames as well. If we need a frame and we're taking a frame away from another process, then we need to know who is using it because A, we need to do the stuff we just talked about, make sure we save the contents of the frame to the appropriate location, and B, we need to update the MMU page table entry for the victim process to make sure that they will fault the next time they access that frame. I'm sorry, that page is really the right term to use. Okay. So, again, what does this tell you about what should be in the frame table? Well, at the very least, we need to have one entry per actual frame in the OS. We need to know if it's in use or available. And if it's in use, we need to know who's using it. Those are kind of the things that we need to know. Okay. How you decide to implement that is totally your call. But you probably won't make a horrible choice as long as you make sure to have all of that information. Okay. Obviously, this is all complicated by sharing binary data. Okay, so I'm going to go through the suggested order of implementation, and then I'll talk about concurrency issues. So I just want to show you what the assignment says about order of implementation and tell you why. They say implement the frame table first. So basically what they're saying is don't change anything about the way the OS works, except make a frame table and start recording what frames are in use and by whom. Okay. This basically allows you, this is like sort of setting up the shot, if you will, on a pool table, to allow you to start making allocation and eviction decisions down the line. Okay, so this is starting to build the first little bit of the paging system. Okay, you won't have any swapping, you haven't built it yet. You won't have eviction yet. Who cares? So some of your tests will fail, but that's okay, just panic the kernel. Okay, so then make sure all the tests pass. That's really crucial here. So far all we've done is added the ability to record what frames are in use and who's using them. Okay. Next, we do the supplemental page table. And it's funny because a lot of the code that you need for this is actually going to be in process.c already, because it's basically the stuff that initializes the address space. That's instead going to initialize your supplemental page table. And then the code that actually loads the address space, something like it will move to your page fault handler. Okay. So now we're doing our first step into demand paging. Okay. So that's the next step. Okay. Yeah, so like I say here, instead of allocating the pages immediately, we record what should go in those pages so that when we get faults, we can load frames and do so. Okay. And so this is sort of the first step into demand paging, getting that whole mechanism up and running. Okay. So yeah, you don't have eviction, but again, make sure all your Project 4 tests pass. This is really crucial. Okay? Because see, what I'm saying here is you make a little change and then make sure it still works. Make another little change and make sure it still works. Because if it stops working, you know exactly what you changed and you can look at it. Okay? Third one, now it says you can start doing things in parallel. This is where it gives me the willies, because any one of those things that you do, implement it, and then make sure that all the tests pass. Don't make too many changes and then get stuck having to debug a massive amount of code. Okay? Some of those things are more difficult than others too. So, you know, if you feel really ambitious, then you can tackle a big one. Otherwise, you can tackle a smaller one. And just make sure you get things working. Finally is eviction. Okay? This is where a lot of the concurrency stuff really starts getting tricky. Okay. So, because this is where the concurrency starts to really show up. They say you can have a simple paging policy, and they suggest random eviction. I've seen a lot of students say, well, I'm just always going to evict page 0, or frame 0. Please, like I say here, please don't do that. Okay? And I'll tell you why. Because you'll run it, and 20 minutes later, it won't have finished running, because it's just hammering on frame 0. And it's running terribly. Okay, so I'm just telling you from experience of watching students have fun with this. At least do a random eviction policy so that you get some base level of performance from the system. Okay, so just make sure you do that. Let's see, policy. You basically are only required to implement something that approximates LRU. And then it's funny because they turn around and say, try clock, for example, and that's not hard at all, okay? I think that any of you should be able to figure this out, especially like you can use your frame table, you can chain things together, or you could just have a clock pointer that goes through the frame table if you want to do that. There's a lot of straightforward ways to implement clock in this system. Notice it doesn't require an interrupt handler. You don't need a timer tick for clock, even though clock is right in the name. So, you can do something more sophisticated if you would like. I'm not sure that I would recommend that, but you certainly can. I will give bonus credit, probably not a lot, but again, if you make a little bit of extra effort just because you're curious or a glutton for punishment, then I'll probably reward it. Like anything with a timer tick is part of the policy implementation. I'll probably give a couple of points of extra credit to. And anything adaptive will get significant, like probably 5 points or something. It depends on if it's really, really pretty, then you might get more. But I don't want you to focus on policies. I want you to focus on getting everything working, because it's hard enough. Okay? So again, simplify your life. Any questions? Okay, last thing to talk about, and we'll probably go a few minutes over, and I apologize for that. You have several operations that can definitely be preempted by other kernel threads running. Okay? Again, think about the operations that have to occur. You take that page fault handler and just decompose it into the steps required for each one. You can develop quite a sophisticated outline. I'm not going to do that for you because this is your exercise for this assignment. But you have to find an available frame to use. Okay, so that I'm going to have to look at frames. Finding an available swap slot. That'll require scanning through maybe a bitmap to figure out which slot is available. Evicting a page from a frame because that'll include I/O, or loading a page into a frame. Okay. Concurrency requirement was if it requires I/O to resolve, it should not block things that do not require I/O to resolve. And the real key here is don't be holding some global lock while you're doing I/O. I mean, let the device controller hold the lock, and then you let other things go. Okay. So basically, you can do this entirely using locks. The solution implementation only uses locks. So I wanted to give you that giant hint because when you're looking at this, you may say, "Oh, I've got to come up with some." You really don't. Leave the crazy synchronization crap to next assignment because that's where you'll have to do that. If you have a timer-based policy, inside the timer tick handler, obviously interrupts will be disabled, but otherwise the grading guidelines actually say take off lots of points if you have to disable interrupts to make this work properly. Okay, so just be aware of that. Yes, sir?
In the last assignment, there was notice that like the file system was not re-entrant.
Yeah.
How does that factor in here?
The file system is not re-entrant. You'll actually be interacting directly with the swap block device for this assignment. So it actually won't interfere with the concurrency requirements of this assignment, which is kind of interesting, but that's why you can have a global file system lock and it doesn't interfere with the virtual memory.
What about like loading like executable file?
Mm-hmm. That's an interesting question, and I don't remember. Well, again, I mean, you're doing an I/O operation, and it's okay if that blocks other I/O operations, but it shouldn't block other page faults that don't require I/O. So the global file system lock would just be a second level of serialization for page faults that require it, but it shouldn't interfere with page faults that don't. Okay, if you have more questions about that, we should definitely discuss later because that's probably a rich topic for discussion. So you should feel free to introduce locks for guarding large operations. Again, giant hint. I'm trying to find a swap slot, maybe have a lock for that. I'm trying to find a frame, have a lock for that. Okay. And like I say, it will limit the concurrency of the virtual memory system, but it's not required by the assignment to be more sophisticated than that. Just don't hold one of these locks guarding one of these operations when you perform I/O. So again, when you need to perform I/O, try to have a finer grain lock. Now, I want to mention that frames are where we're going to run out of time, so I'm just going to warn you about that right now. Yeah, it's 1:58. Basically, just to describe the issue, let me throw this up here. Process A, false. It evicts process B's page because it wants the frame. So it starts to load data for process A into that frame. So it blocks. The kernel decides to start running process B. And that process faults on the page that was just evicted. What do you do? Okay. This is the classic scenario you need to think about. There's lots of details so you can reason about this for yourself. But should you avoid having a fault? Should you allow the fault? How do you block process B to make sure that it can't proceed until the eviction completes and then it can go ahead and load the page into another frame? Okay, this is a classic example. You'll have to explain this in the design doc. So if you reason through this scenario, and again, notice this doesn't show up till the end when you have eviction, then you should be able to come up with a design that avoids the issues that this illustrates. Okay, so locks in individual page frames is a great idea for solving these kinds of problems. And I wanted to mention that, and I also want to mention that there's actually a try lock acquire that you can use as well as lock acquire. And this allows you to use locks as pins. So basically, if you try to acquire a lock on a frame and the lock is already held by somebody else, this will just return false and you can just go on. Okay? So you can use that. You can also see if a lock on something is held by you. Okay? And sometimes this can be helpful as well for resolving certain concurrency issues. But basically, you can use all these tools to figure out how to synchronize in these situations. Okay? So this hopefully will help a lot in figuring out the concurrency. Yeah, so finding an available frame for paging, you can try to acquire each frame's lock in sequence. The lock is already held by some other thread. The attempt will fail, just go on. If you find a frame, you grab its lock, then you can release the global lock you were using to traverse the frame list, and then you can do your paging into that, and now you're not blocking anybody else. So these are the kinds of things you can do to avoid blocking others on I/O. Okay, questions? All right, I know this is very rapid. It's the first time I've given this lecture, so there's clearly some practice needed. 2 final notes. One is make sure you follow a separation of concerns. Most of the time when we see people's implementations, there's frame.c, page.c, and swap.c, if you will. Okay, so people will do that. They tend to expose simple operations to perform these things, and then you just assemble the pieces together. Very important for this. Make sure things are well documented as well. That'll help you as well as us. The solution implementation does this, and then it's really understandable to read. So I think you'll find that as well if you follow a modular approach with this. And then the other thing is just make sure that you test after every step. That's the whole point of the suggested implementation. Make sure you test after each step so that if something completely blows up, you know exactly what you changed and you can try to fix that. That's going to be really important to making this a tractable lab. Okay, any questions? Thank you for being subject to my experiment. I hope it will be helpful. Please let me know if it's not. And next time we'll finish off our general discussion of virtual memory next time. So we are done.